Hi, welcome to my SauceCon presentation. My name is Jim Whitehead, and I'm the Chief Scientist with the AutonomIQ division of Sauce Labs. Today I'm going to be giving a presentation on how artificial intelligence is impacting software testing. Now, before we get excited about what artificial intelligence can do, I think it makes sense for us to step back and ask ourselves, what can human testers do? Well, a human tester, when faced with an application, they have to go in and understand screens and be able to determine, okay, what are the buttons? What are the forms? What are the links? How do they get from screen to screen within that application? Once they understand that application, they have to develop scenarios of use, like how can you knit various screens together in order to exercise useful capabilities of that software. You have to create synthetic data in order to enter into form fields and to be able to get from place to place within that application. And then finally, you have to understand whether the application is working correctly or not. Is it behaving as intended? Well, if human testers can do that, you would ideally like artificial intelligence testing to do the same. And in particular, artificial intelligence testing really needs to be able to create synthetic test data so that it's possible to put data into all of those form fields, all of the data entry fields, search fields, username, password, you name it. You have to be able to enter data into those in order to be able to go from screen to screen within an application. And then once you have an understanding as an artificial intelligence of the various screens of an application, you have to be able to combine those together to be able to create test paths through an application. By combining that synthetic test data with those test paths through an application, you're able to automatically create software tests. And in particular, my work at Sauce Labs is really motivated by this question, which is how far can we automate testing of web and mobile applications? Is it possible to just point an artificial intelligence at these applications, let it go for a while, and have a whole bunch of really smart and useful test cases come out? Well, I have to say, we're not quite there yet, but we have some really promising work, and I'm going to be sharing with you some ongoing work that we're doing here at Sauce Labs in the area of synthetic data generation. And I'm also going to be sharing with you some information coming from the research literature, research projects that are taking place in universities around the world, where people are pushing the boundaries of artificial intelligence and testing. And we're very excited by those ideas too, and we're thinking about how can we bring those latest advances into the various products that we provide at Sauce Labs. All right, starting with synthetic test data. So synthetic test data generation has a bunch of different challenges. You need to be able to create data for a bunch of different common fields. So names, addresses, passwords, email addresses, social security numbers, credit cards, you name it. You also need to be able to go beyond those commonly occurring data types to be able to generate data that's specific to one kind of application. So if a particular application has a particular kind of product name or product SKU, you want to be able to generate those as well. Sometimes there are very complicated dependencies among fields that you're trying to generate. For example, if you're generating the names of people in a family, it's very often the case that the last names of at least some of the people in that family are shared and are the same. As well, we live in an international world, and so your data generation needs to be able to handle things like generating names in many different many different countries. You would ideally in your data generator like to be able to learn from data when you have it available, but you also don't want to have to depend on having lots of examples of data. Ideally, you want to just be able to look at an application, generate some data based on your understanding of those form fields, and just go. So both working with data when it's available and not working, or working when you don't have access to that data, both of those are really useful. And if you see a form, well, it would be really nice to be able to understand that form in its totality and to be able to generate data for it. And finally, if you have that opportunity to generate complicated documents, boy, that would be pretty cool too. All right, so let's start off. So the simplest case are for synthetic data generation are single field generators. So this is where you are, say, picking a single field within a form and you want to provide data for it. So in this case, you assign each form entry field with a particular single field generator. And this approach works really well up until the point you start having dependencies among those fields. Once you start having one field depending on the value of another, well then this approach of kind of assigning a single field generator to a particular field, that starts to break down a little bit. And so here on the side we have an example of a single field generator that generates an American state. It's just randomly picks a value from a list, and in this case, to make things simple, we only have 3 states. Okay, but you can have single field dependencies where the value of one field depends on just one other field. And so in the example here, we show how the towns that we're outputting from this particular generator, the set of towns varies based on what state. So if the previous field generator generated the value California, well, then we would pick from between Santa Clara or Cupertino for our towns, and so on. And so this can be useful for those kinds of geographic limitations where, like, a particular city only appears in a certain location, or postal codes are often very geographically limited too. Okay, so that works well when you have pretty common data types, kind of states, different cities, but very often applications will have domain-specific data. There's something about the particular business that led to that web application or to that mobile application, and they need data that's specific to that particular business. You're not usually going to find some off-the-shelf generator that works for that, so instead, you want to be able to create a custom generator that's very finely tuned for that. We've been taking a look at a technology called tracery. And tracery is interesting. It's what's known as a generative grammar. Now, computer scientists may be familiar with grammars as a way of accepting a language. So you have strings in some language, it goes into a grammar, and then it tells you whether it matches that language or not, and it gives you a parse tree out. But a grammar can also be turned around, and it can generate strings in a language. And it's in that sense that we're talking about generative grammars. Tracery was designed for use by artists to be able to create things like Twitter bots or to create text or simple dialogue within computer games. But it happens to be really well suited for very quickly and effectively making domain-specific data. Here on the side of the slide, we see a very small grammar which is intended to generate the description of various kinds of snack foods. Maybe we're testing an app, a shopping app that's focused on these kinds of snack foods. So some of the outputs are there in the bottom. It can produce like snack-sized Snickers or trial-sized Snickers, or maybe a large peppermint patty. And so you see that you have kind of a size adjective, and then you have the type of the snack. Well, up in the grammar up top, you can see that there's kind of this, hash size and then hash snack type. And then those are essentially saying, when you get to that place, go down to that particular production and then randomly pick one of those elements and then put it in. And it's possible for, those additional elements, like here size is just a bunch of exact strings, but we could in fact have size call out to yet another production and another production and so on. And so these productions can branch out. And as you start getting even just a little bit branchy, you get a very large amount of possibilities for a pretty low amount of authoring. And as you can see, the syntax is pretty easy to use. It's pretty straightforward to pick this up and generate data for your projects. Tracery is created by Kate Compton, and you can get access to this from the website tracery.io. And there are language bindings in Python and JavaScript, among others. Now, writing a grammar can be a little tricky. You have to understand that grammar syntax, and there's some trial and error involved, and you can sometimes generate kind of a bigger set of data than you want and have to kind of tune that and rein it in a little bit. It would be really convenient if these grammars could be just plain written for you. And so that's the idea behind an approach called grammar induction. The idea of grammar induction is that you give a grammar induction tool, and so one that we're going to talk about here is called GITA, which stands for Grammar Induction Using a Template Tree Approach. And GITA is very handy in that it can output tracery grammars. So you provide a bunch of data into GITA, it goes ahead and does its grammar induction work, and then out the other side comes a grammar that is capable of producing any of the test data that was provided as input to it, as well as a whole bunch of different permutations of it. It sort of essentially learns patterns within that data in that process of grammar induction. And so then once you have that grammar, well, you can go ahead and generate a large amount of test data to your heart's content. Okay, what does that look like? Well, here is an example of some sample data coming in. You have a whole bunch of different addresses here, and it goes into GITA, and it is able to learn this tracery grammar, and some particular sample outputs are there. And you can see how the roads end up, picking out of the set of roads that were in the sample data, but they're being combined with different street numbers, different towns, different zip codes, and so on. So it is kind of mixing and matching the data that it sees from within that data set. Now, one challenge or one problem here is that the sample output is reproducing exactly some of the elements of the input. And so if you really do need to completely anonymize the data that you're using for testing, well, then this kind of grammar induction approach wouldn't work. Okay, so at this point, we have the ability to automatically generate data for single fields. We can have those fields have dependencies on other fields. If we're running into domain-specific data, we can automatically generate that using grammars. If we have a lot of data available, well, then we can automatically generate a grammar for you. And so then, you might think, well, gosh, we're now ready to go ahead and start generating data for forms that we might see. And indeed, that is true. But right now, you would need to, as a human, automatically assign a generator to each form field within a form. And again, our goal is to be creating this artificial intelligence tester where that kind of work would be performed for you automatically. So the question is, well, is it possible to just take a look at a form and be able to, from things like the title of a particular field or the overall structure of that form, be able to try and determine, okay, what is the data type for each element in that form, and based on that data type, can we assign a generator to it? That is, can we just look at a form and be able to automatically generate synthetic data for it? And the answer, I'm happy to say, for certain classes of relatively simple forms is yes, absolutely we can do this. So let's take a look at how that might work. The project that we'll be talking about here is one called Formosaurus. It's available on GitHub. And it follows roughly this pipeline that you see here. So you start off with a web page, and then there's a process by which there's feature extraction from that web page. The extracted features then go into a two-step process. There's two different machine learning classifiers that are working here. The first machine learning classifier does form detection. So it ends up looking at the information from that web page and then saying, oh, okay, I bet I can figure out that this is a login form, or I bet this is a shopping cart validation form, and so on. Once the form is detected, then that information goes along to field type detection. So both the form type as well as information about each individual field is used to try and classify the data type for each field in a form. So is that first field for a username? It is the second one for a password, and so on. Once you have that information, well, then you can go along to data generation, and you can be doing things like say, okay, if I know that this is a name field, well, I have a name generator, and so I'll just automatically assign that name generator to that name field. Okay, so let's dig in a little bit into each of these blocks in this pipeline. So for the feature extractor, it goes ahead and looks inside the web page and says, oh, okay, I'm going to make counts of things like, well, how many text area widgets there are and how many input type equals checkbox elements are there. Similarly, how many input type equals email elements are there, and so on. And so it gets these counts, and then it's able to pass these counts into the next step, where it runs it through a logistic regression classifier. It's a machine learning technique. And then it tries to bin that form into one of several possible form classes. So this could be a search field, a search form, a login form, a registration form, and so on. You see a pretty complete list of it there. Okay, then finally we go into the second classifier, which is for the individual fields. Here it turns out a conditional random fields classifier works the best. And some of the many possible field types that you can have are things like username, password, email, CAPTCHA, and so on. Okay, so what does a form to generated data example look like? Well, let's go back to that form from the beginning of this section. We have volunteer registration. We have a name, first and last, email, birth date, phone number. Well, if we run this through Formosaurus, and these are the kinds of fields that it knows how to detect well. It's a very well-behaved form. It has nice labels for each of those form fields. And so Formosaurus did just an excellent job in picking these out. And so it came back with the following labels, Q3 name first, Q3 name last, Q8 email, and so on. Based on these, it's then possible to assign generators for each one of these fields. And so, first name and last name are ones that come out of a library called Faker, which is really useful for synthetic data generation. For a month, we created a list generator where we just picked a random month from a list. For things like the birth year, that was assigned to a random number between 1920 and 2021, and so on. And then finally, in the far side, we see that list of generated data. And that's just one example of many of data that actually was generated by that generator. Okay, so that ends our discussion here on synthetic data generation. But if you're interested in learning more, well, for one, one aspect of synthetic data generation is called fuzzing. Fuzzing is often used to create both positive as well as negative test cases. We've been focusing here just primarily on positive test cases because positive test cases are very useful for getting you from field to field and navigating through your application. But fuzzing in general is an approach for generating both positive and also negative test data. And it's often used more at a unit testing level. But there is this really excellent and freely available book called the Fuzzing Book. And what's nice about it, besides the price of free, is that it also has a number of Python notebooks available. And so you can follow along with the techniques that are described in this book within your own Python notebooks. And then also just wanted to throw out a recent-ish paper, this data synthesis based on generative adversarial networks. It introduces a technique called table GANs. And the idea is that if you have very large amounts of data, then it can sort of learn the distribution of that data and then reproduce data that's similar to what you trained on. But it's very nice in that it also has the quality that it's not susceptible to trying to reconstruct information about those people. So if PII, personally identifiable information, is really important to you, well, then this table GAN approach is going to be really nice because it can give you synthetic data that matches the original frequency distribution, but without exposing any data about the people. The downsides, you need a fair amount of data, low tens of thousands of instances to do the training, and the training takes a fair bit of time. It's a relatively sophisticated approach. Okay, so we know how to generate our synthetic data. We're well on our way to making our AI. But now we want our AI tester to be able to automatically make paths through an application. We want it to be able to actually create full-on test cases where it's navigating from place to place to place in that application. All right, so what this gets down to is there is this need for testing paths. Applications have multiple screens, and any really meaningful test involves you doing data entry and navigation through multiple screens in order to test some particular functionality of an application. So if you're going to do full test automation, well, you got to be able to come up with these test paths and have those test paths be meaningful. Okay, well, the general approach that people use for this is called model-based testing. So what you do is you end up creating a model of your application, and the model takes the form of a graph. And in your graph, you have states, these are the nodes, and then you have transitions, arcs between those nodes. Generally, the nodes represent different states inside your application. A state can really vary from app to app to app. A lot of times, but certainly not always, a lot of times a state represents a particular screen. But if you have a very complicated application where a screen can modify and change quite a bit based on the data that you're entering into it, well, then you can actually have many different states even within a particular screen. But, as a first rough approximation, as you're just thinking about this for the first time, you can kind of equate a state with a screen. But you should be aware that it's more complicated than that. And then the transitions generally involve entering data into the application. Now, sometimes an application will receive some event from the outside world, or maybe a timer will go off and it might change from one state to another on its own. But in general, an application will change from one state to another by the user providing some kind of input, by the user asking it to do something. So broadly, we have our model where we have these states. The states represent often screens or different important times within a screen. And then we have transitions, which represent providing input into the application. If you have a big enough model, well, what you can do is you can start from some start location, usually like an entry screen or a start-in screen or a home screen. And then you just start doing walks through that graph that are legal. And so you go from one state to the next state, to the next state, and to the next state, and so on. Once you have traversed all those different states, well, then you end up having a viable path through an application. And once you have a viable path, well, then you can unroll that, and then you can start issuing commands to that application using your favorite test automation framework. In order to do this, well, okay, you need to have that model with the states and that walk through the states in order to figure out what your path is going to be. But then also those transitions often depend on data, and that data is coming in the form of synthetic test data, hence all that work in the previous section of this talk. So here on the slide, we do have this example of a very simple model of an application with a couple states. And this is provided by an open source model-based testing tool called GraphWalker. And people have successfully used GraphWalker to test web applications and I believe mobile applications as well. Okay, so far sounds good. Just kind of whip up a model, run it into one of these model-based testing tools, which will figure out the paths and output test cases. You're done. You've now done automated testing, right? Well, okay, yeah, there's a bunch of challenges here. So first of all, creating these models in the first place, once you get beyond just these very simple ones that you often see in tutorials, they can have very large numbers of states, and it can be very complicated to create them, to understand them, and to maintain them over time. In order to do this at all, you need really sophisticated testers. And those sophisticated testers, are not, they're not cheap. So as a result, really you'd ideally like to be able to, as an AI, to be able to create these models automatically. And if you could automatically create one of these models, well, then all that complexity of creating the model and maintaining the model, that kind of goes away. You just recreate the model whenever you want. You also need to be able to create that test data for the transitions. And again, that's where the synthetic test data comes in. And then finally, once you have this model, you can generate huge numbers of tests, but maybe you don't want huge numbers. Maybe you only want kind of a small number of tests that do the very best job of finding bugs or exercising all the capabilities in that application. So there's some intelligence in picking the right test paths as well. All right. In general, model-based testing is a very broad area, but let me talk about one project that had a fair bit of success in doing this in an automated way for web applications. So the project called CrawlJax. It's a little bit older. It's about a 10-year-old project at this point. But it really embodies this model-based testing approach. So within CrawlJax, they built this graph of web application states, which they called a state flow graph. And then, once they built the state flow graph, they ended up, combining duplicate states or combining similar states to sort of compress the size of that resulting graph that they created. And then they did have an approach for, walking through that graph. And, sometimes as they were doing those walks, they would discover new states in that state flow graph. And so they would add those, and they would then be available for other times when they need to go through and, create new test cases. This work had a couple challenges. So one of the challenges that they faced was coming up with the test data in the first place. At that time, they didn't really have access to very sophisticated synthetic test data. And so a lot of what they were doing was kind of just randomly entering text into text fields, and then they were just kind of finding any button that they could on screen, and then they would just go ahead and exercise those buttons. So it was a little bit of a random walk on each screen, trying to figure out, okay, how do I press these buttons and do things in order to get the app to move on. These days, you could use synthetic test generation and things like Formosaurus to be, much more intelligent about it. The other challenge is detecting new states. It required this ability to do a comparison of two states, essentially a differencing of states, and that often required application-specific differencing logic. It was hard to do a general purpose, state differencer for some particular application. But again, there's been a lot of improvements in that in the intervening years as well. And then, here's an example of what one of these state flow graphs looks like, with various states as the nodes, and then with various actions taking you from node to node. All right. There have been a lot of research projects that have focused on automated app testing for both web apps and mobile apps. So there's this nice systematic literature review. This is really focused on the research literature. So you should be aware that, most of the systems that I talk about there, they're ones that, maybe they have some code available, but these are not products that you can just, take and start using. They are often a little bit out of date. And so it's, more, I think, better to kind of read this and get a sense of ideas and potentials. It's, there aren't as many systems in there that are going to be readily usable. And then just more for fun, this very recent paper called Drift, where they used deep reinforcement learning for navigating through the user interface of a large application. And so in this case, they were focused on Windows and screens within Windows. And what they were trying to do is find a bunch of paths by which they, essentially create that big state graph and then quickly find paths that accomplish certain goals. And they were able to find that, this reinforcement learning approach, when given enough time to train, was able to be very, very effective, far more effective than just random walks in terms of getting from, say, the start screen of Windows to a particular ending screen throughout. So then anyway, if you really want to see, okay, how much you use reinforcement learning in this automated testing domain, there's an example. All right, so that's the end of my talk. Hope you enjoyed this walk through, synthetic data generation and approaches for model-based testing where you automatically figure out what those graphs look like. Be happy to answer any questions that you might have. Thanks for listening.